For the electric utilities, grid reliability may require the monitoring of millions of devices across an ever-changing landscape of electrical circuits servicing hundreds of thousands or millions of customers. The utility's goal is to first and foremost deliver electricity safely, reliably, and efficiently. I'm Tom Anderson, Principal Systems Engineer of the SAS Energy Division. Today we'll be discussing driving energy efficiency through improved asset management. We'll walk through the generation, transmission, and distribution systems of an electric utility and describe its operation, and demonstrate how SAS Analytics can be used to improve energy efficiency through analytics. Shown here is the process of delivering electricity as described by the U.S. Energy Information Administration. Power plants generate electricity that is delivered to customers through transmission and distribution power lines. High voltage transmission lines, such as those that hang between tall metal towers, carry electricity over long distances to meet customer needs. Higher voltage electricity is more efficient and less expensive for long distance electrical transmission. Lower voltage electricity is safer for the use in homes and businesses. Transformers at substations increase or reduce voltages to adjust to different stages of the journey from the power plant along long-distance transmission lines to distribution lines that carry electricity to homes and businesses. It will be this distribution network that we'll be focusing on today. The distribution grid or network is responsible for delivering electricity from the substation to homes and businesses. As shown on the right, it consists of many nodes and connections that assemble the network of circuits. In our demonstration today, we have 11 substations that support over 90 circuits. Each point on this map represents a node or connection where the transformer or other device resides. Distribution transformers step down the voltage delivered to customers. We have over 1,700 transformers within these circuits. Other devices include fuses, switches, and reclosers that are in place to maintain a level of safety, security, and reliability. Understanding the ebb and flow of energy across the network is key to enhancing energy efficiency, reliability, and safety. The distribution of energy is based on the circuit designs and have physical limitations of those circuit devices. Increasing energy assets like electric vehicles, solar arrays, and battery stations are impacting those limitations and configurations. Using analytics and devices in the field, SAS can enhance the energy efficiencies of those circuits. When considering energy efficiencies, utilities must have accurate information about system performance to ensure that maintenance dollars are spent wisely and that customer expectations are met. To measure system performance, the electric industry has developed several performance measures of reliability. These reliability indices include measures of outage duration, frequency of outages, system availability, and response time. The most often used performance measurement for a sustained interruption in the system is the System Average Interruption Duration Index. This index measures the total duration of an interruption for an average customer during a given period. It is normally calculated on either a monthly or yearly basis. However, it can be calculated daily. The System Average Interruption Frequency Index is the average number of times that a system customer experiences an outage during the year. Once an outage occurs, the average time to restore service is found from the Customer Average Interruption Duration Index. And the last index we are highlighting here is the Momentary Average Interruption Frequency Index, the average number of momentary interruptions that a customer experiences during a given period of time. And momentary interruptions are generally less than 1 minute of interruption. There are other indexes used as well, but these are the ones that we are highlighting today. And utilities track these indexes to determine how well they are performing. Utilities continue facing new operational challenges as there are expansions and new devices added to the system daily. Expectations from customers and regulators are always increasing as well. To meet those expectations, Utilities are continually looking for new tools and opportunities. And now we'll demonstrate how SAS can drive energy efficiencies through better asset management with the ability to read in potentially thousands of devices on a complex smart grid metering infrastructure to determine health and worthiness of circuits. The focus of our demonstration is going to be line distribution transformers. As I mentioned earlier, these distribution transformers are generally mounted on poles or pads out in front of homes or businesses, and there's no information being collected from these. These are just devices out in the field. But we're going to be using the AMI meters that are being serviced by these transformers to use their data to assess the transformer itself. Each transformer will generally have anywhere from 1 to 10 meters it would be servicing, and we roll up that information to determine the total load and capacity being used on the transformer. The reason why we've chose these transformers is because there are costs associated with these when they go out. The distribution transformer can range from $1,000 to several $100,000, depending on the size. The increased proactivity of predicting these transformer failures can help reduce the cost of OEM and increase the system reliability, basically make those indexes that we're assessing much better. Streamlining and planning the coordination required for these transformers can also be done. Again, keep in mind that these transformers, there's generally hundreds of thousands of these located across any particular grid or network that a utility would be servicing. Here's an example of a reliability dashboard, where we have the indexes across the top, along with reports on the types of causes of outages, and looking at 5-year trends. And these are common reports that would be used by a utility. Here we're looking at causes trending over 5-year periods. And here we're looking at the comparison of interruption causes by comparison over an hour. So what are the average hourly interruptions that are happening based on the circuits in here? As well as looking at the cause history. What are the types of causes that we're mainly having? Are they prearranged? Are they underground malfunctions or overhead malfunctions? Driving deeper into the reliability reports, we can select a substation and look at the substation's performance based on the transactions happening on a particular circuit. These are the circuits that are listed here, and we have customer interrupted values and customer minute interruption values, as well as duration values in here. All of these are used to calculate the indexes that we have shown here on the right. And comparing these indexes like SAIDI and SAIFI, we can look for outliers. And when we have outliers, those are indicators that we probably have something within that system that we need to address. And in some cases in here, areas like overhead malfunctions are identified that are probably happening over in a reoccurrence time that we want to address or look at. Other reports, such as outage incidents, as we see here, we're looking at 2018. We're looking at a substation called ERIC and the different causes and components that are happening over time. And then comparing those also with the weather elements that we have. So types of outages that we have and what are the occurrences of the weather that are happening within those. Down below here we have the substation name and the devices. And the devices that had the most duration of outages that are happening here. Highlighting these, we probably wanted to look at these particular devices, such as transformers and locations, to determine what's going on with those particular assets. And using the data that we have collected, we can create asset scorecards, where we actually score the transformers or score the devices for propensity for failure. And in this list here, I have a list of top 100 transformers and their score. A score of 0.8 or higher indicates that we probably want to have an inspection done on that particular unit or the transformer that's out there. On the right-hand side here, we have substations that we can look at based on outages that are occurring. By selecting those, we can look at the types of outages that are happening, as well as look at the durations of those outages and the types of outages that are occurring on those systems. Now, being able to create these types of scorecards is done by applying our machine learning algorithms, such as decision trees, random forest, or gradient boost. In this gradient boost example, we're looking at transformers, and we're taking in variables such as the load over a particular period of time. We bucket the load into 6 hours, 12 hours, 24 hours, 36 hours, and 72 hours. We take in values like weather as well. And these are the variables of importance that are used to determine the propensity for that particular failure or challenge that they're having with a transformer. And now I'm going to demonstrate how we can operationalize that gradient boost model that we created to score those transformers in real time and drive the energy efficiency analysis to improve the asset management that we're doing. Here I have the gradient boost model. My response variable is the event flag that I have assigned for this. Now, an event identifies when a transformer has gone overloaded or has caused for a failure. My predictors are going to be the data that I've collected from those AMI meters. Those are running values that I've bucketed back 72 hours. And that bucketed information represents time fields of values based on load, variance values, median values, maximum values, and also weather data with those same bucketed fields. I also have indications in here when the transformer has gone over 100%, over 120, 140%, or over 150% of time. Now, selecting those variables and those predictors, I have my gradient boost model as defined by my selections. And here you can see the variables of importance. Those variables, those values that made the most impact on my event flag. Items like the variance over 6 hours. So how much fluctuation did I have in a load over 6 hours and in 12-hour periods, as well as what was my value for total load at the 6-hour period. Other items in here include that dew point values, as well as the type of transformer that I'm using. All these are the factors that are laid into my gradient boost model to determine whether or not I have a failure or a possible challenge. If I like this model, I can then create this model and move this into model management and then promote that into other sources like event stream processing, which is what I'm going to do now by creating a pipeline. By right-clicking and selecting Create a Pipeline, I can create a new or existing project. Going into an existing project, you can see my process flow as it appears here that was just created in Visual Data Mining Machine Learning, where I'm taking in my data, it does some imputations and performs a gradient boost model that I designed in there. I've also created other pipelines, other processes to do the analysis on here for comparison. Some of these processes included other regression type analysis, as well as more advanced processes like neural nets, for decision trees, and random forest as well. Creating a pipeline comparison of those, SAS will help me determine which of those pipelines, which of those models perform best. And here you can see from the models that we were producing, I have a couple of gradient boost models of neural net and decision trees. And you can see that this particular gradient boost model was the one that was championed. From this process here, I can go in and view the code that was created, as well as the output that was developed from my modeling practice. By publishing this model, I can make it available to other third-party applications, as well as SAS Event Stream Processing. So going into SAS Model Manager, I can select the projects I've created. This is the asset management model that we've worked with. And you can see my models that I've created. And from here, I can view the variables and properties, see the performance and the history of the values, and also have different versioning as required. My gradient boost model is the champion model. And by making that available in Model Manager, I can now access that into event stream processing. Event stream processing allows me to take streaming data at real-time occurrences and apply my models to that streaming data at tens of thousands of cycles per second. In here, I have a project that I've created, Grid Reliability. And when I open this up, we'll see the different inputs that I have from my transaction data from the utility grid. These are 6 different circuits that I'm displaying, and from these circuits I'm bringing in transformer information and AMI meters. And then I'm combining that transformer and AMI meter with the weather data and bucketing that information, joining them together, and then applying the calculating node that applies the gradient boost model that we've created. Here you can see calculating, select the SAS Model Manager, where we publish the model. And in my repository, I have several models I've created, in particular my gradient boost from the grid reliability model that we've created. Here you can see the different models that we've published, including the neural nets and decision trees. And we selected the gradient boost model, which was the champion model that's selected. From that output, I do some filtering for flags and alerts, combine the information together so that I can report geospatially the locations of those transformers that may be in distress and aggregate for further alerts. And let's demonstrate that process. Going to my ESP dashboard. We open the dashboard, and we can see from that network diagram that you probably recall, we have all of the different nodes from those circuits that we were reporting on. These are all of the reporting transformers in real time. Over here on the center left, upper center left, is the location of transformers that have scored where they probably have some sort of challenge on them that need to be addressed. This is the streaming data that we're showing, bringing in the transformer information and the values that are being scored upon, including the gradient boost output values. Using SAS reporting and analytics, we're able to score devices in real time on the utilities grid distribution network, improving the efficiency of analysis on asset management in real time. Thank you for spending this time with me today. If you have any questions, please reach out to me at tomanderson@sas.com. Thank you.